Okay, so have you read the questions? What's the answer to the first part of first question? It's straightforward. It's related to Hooke's law. We have a plot. This plot gives a relationship between force and extension in the spring. So we have extension represented by L on x-axis, and then we have tension represented by T on y-axis, and the graph looks like this. Okay, so this point, it's at extension of 10 centimeter, and then we have tension here on the y-axis at 10 centimeter. Origin of coordinate is 0, 0. So the first part asks if this plot represents the Hooke's law, if this obeys Hooke's law. How do we know if it obeys Hooke's law or not? Do you have any idea, any clue? Like, how can we look at a plot, a graph, and tell whether it obeys Hooke's law or not? That's like a more general question. How do we know that if this plot obeys Hooke's law or not? And I can give you a mathematical form of Hooke's law. It is F equals minus K times X. So X is extension here. In this plot, it's represented by length L. K is a spring constant, so this is extension. This is spring constant, and this is applied force. This is F applied. So, for example, in this question, the case the object under discussion is a spring. Okay, so we have a spring, and you apply some force on spring. So this is the force that you apply to stretch the spring. This is called F applied, the applied force. Okay, the right hand side, which is equal to minus K times X, this side gives you the Hooke's law. So this, if you may want to call it, you can call it FH, which means this is the force which Hooke's law tells you. So you see the force, and this is the force that spring applies in response to the applied force. So you have a relationship with the negative sign. We will come to that, what that means, but at this moment, we are just supposed to tell that whether this graph represents the Hooke's law or not. And this is the expression for Hooke's law. So you had a spring, you have applied some force, it got some extension, and the extension follows this kind of pattern. This is the graph between applied force. In this case, they are calling it tension. Supposedly, you have attached a spring to the spring, and then you are pulling with the help of spring. So since the forces in springs are called tensions represented by T, so we have a graph T against this extension, this relation. So this F applied in this case is T. How do we tell from this expression or from this graph that whether it obeys Hooke's law or not? This is Hooke's law. How do we tell? Yes, please.
If the slope is negative?
We will come back to negative sign. Your answer is right. Actually, you are going to the second part of this problem. So probably you know the answer, but there's one simple thing, like how do we know? This is a simple question. The slope, that's the second part, but your answer is correct basically. But still we need to know precisely how do we tell from this graph that whether it's obeying Hooke's law or not. So there is something coming from mathematics, because we have a mathematical expression here. So this K, it's a spring constant. Its value is fixed once you pick the spring. And spring is made of certain material, so its value is decided by which material you have used to build that construct that build that spring. So it means that the force is just related to the extension that is produced in that spring. This relationship is called a linear relationship. What I mean by linear, you have only one power of x. If you have something like second power of x, that's called quadratic. Then you can have third power or fourth power. Okay, so if two quantities have a linear relationship between them, which, for example, in this case, this applied force and x has a linear relationship in them, then if you plot a graph between them, you will always get a straight line. That's a basic mathematical thing to remember. And once, so here's the thing, like you were given this plot and you were asked whether it obeys Hooke's law or not. You immediately see that it's a straight line, and straight line is always represented by this kind of mathematical relationship in which one quantity is like linearly related to the other quantity. Linearly related means the power is 1. And since Hooke's law is a linear relationship between force and extension, so it does obey Hooke's law. This actually represents the Hooke's law, this plot. If this line were curved, like curved downward and was curving upward, then it was not a linear relationship. If you have a curved line, it's a quadratic relationship, some sort of, but not linear. Then in that case, it does not obey Hooke's law. So yes, it's a straight line, which means a linear relationship between tension and extension, it obeys Hooke's law. Now comes the second question. If it obeys Hooke's law, then you are supposed to calculate this spring constant. Okay, how do we calculate spring constant? We look at the graph, we have some values of extension and tension, and this is a linear relationship, and on a linear like straight line you can pick 2 points to calculate the slope of the line. So a slope, you know, it's mathematically given as change in the value of quantity on y-axis divided by the change in the value of quantity on x-axis, which means y2 minus y1 divided by x2 minus x1. What are these y1 and y2? So you pick a point on this line, so its value corresponds to x-axis is called x1, its value corresponds to y-axis is called y1. Similarly, you pick a second point, value corresponds to x-axis is called x2, and the value corresponding to y-axis is called y2. Okay. So since we want to calculate k, we should have the values of force and x, the quantities which are on y-axis and x-axis. And then you look at your graph and you say, okay, my extension starts at L equals 10 centimeter and it goes up till L equals 20 centimeter, it's given in the graph. And similarly, the force, tension force, it starts at 0 and ends at 10. So what you say, okay, I'm gonna move my points. These was like randomly picked points, x1, y1 and x2, y2. You're like, okay, I'm gonna take my x1 here and y1 here, so I have like right values of x1 and y1. And so you look there and you find that y2 is 10, y1 is 0, that's the start where the y-axis starts. And then x2 is 20, x1 is 10, and you find that it turns out to be 1. Okay, so your slope turns out to be 1, and then you look at the real quantities which are on the y-axis and on the x-axis. We have tension on the y-axis, so tension was on the y-axis, extension was on the x-axis, and you immediately see from this relationship that T by L is actually my spring constant. So slope of this line actually gives you spring constant, which is 1, and then you look at the quantity on y-axis, which is tension, units Newton, and quantity on x-axis, which is extension, units centimeter. So the value of spring constant is 1 Newton per centimeter. That's how you find it. So you see, it's a relationship between 3 quantities, and in order to find one of them, you need to know the values of other 2 quantities. If you were to calculate extension, you should have the values of force and spring constant, and if you want to find force, you should have the values of spring constant and extension in the spring. That's the general way. But the important thing is that Hooke's law is a linear relationship between extension produced in a spring and the applied force. I said I will talk about the negative sign. The negative sign represents that the more extension produced in the spring, the more force you have to apply to stretch it further. You see, if x increases, F also increases. but the negative sign tells you that the force will be in the opposite direction. Like if you are trying to stretch the spring outward, the spring will apply a force in the inward direction. And that's something, if you have ever tried to stretch a spring, you might have observed. It's not only the spring, it's like even the rubber band. If you try to stretch it, you have to apply force, and you feel that the rubber band is trying to contract. It's trying to apply a force in the opposite direction. And that's what negative sign tells you. Just remember that all the vector quantities in physics, whenever there's a vector quantity and it has some negative sign with it, just don't worry about the negative sign. It will just tell you about something about the direction, like which direction my vector quantity is pointed. Because for vector quantities, we need magnitude and direction by definition. Okay, so that's Hooke's law. The second one is stretching and compressing a material, and the statement asked for two problems. The first one is a force stretches a wire by 1 centimeter, 1 millimeter. A second wire of material, it should be same material. A second wire of the same material has the same cross section and twice the length. How far will it be stretched by the same force? Explain. And the second question of this part, second part of this question is, a third wire of the same material has the same length but twice the diameter of the first wire. How far will it be stretched by the same force? Okay, this is quite a complicated problem, but you have to figure out like which are the quantities which are same for all parts, like which are the quantities which are known to us and which of them are not known to us. So let's set the problem. Let's try to visualize it by drawing a wire. So this is our original wire. This wire has a certain length, certain cross-sectional area. This side, this is called cross-sectional area. This is the length, let's call it L. And if we apply a force F on this wire, in let's say in this direction, it stretches it by an amount 1 millimeter. This is the given data of the problem. Okay. Now we have two questions to answer. First question, if I have another wire of the same material but its length is doubled, so I'm gonna make the length double. So if I have this wire, it's the same material, same cross-sectional area in this case, but the length, let me call it L1, this is 2 times L, the original wire, okay? And if I apply the same amount of force F on this wire, what will be the extension in this wire? And I'm gonna call it delta L1, and that's what I want to find, okay? The second question asks, now the length is same as this wire, but the diameter of the wire is double. So this is the scenario for me in the second part. So I have the same wire made of same material. It has same length. So let me call its length L2, and this is equal to L. But the area, let me call it A2. Let's call this A1, and A2 is equal to 2 times. Now, not area, let's call it diameter. So diameter D2 is 2 times D. Let me call this as D1. So this is the diameter, edge to edge length. And its diameter, let's call it D. So this is all the given data. How we are going to solve this problem. So we need to look for one property like this one, like we had spring and spring constant in the first case. You know, spring constant had the property that as long as we keep the same spring, the value of spring constant will stay fixed. Okay, so you apply different force, the extension will change, but spring constant will stay the same. Similarly, we need to have a property for this wire which should stay same under any condition. And that property is called Young's modulus. It's represented by symbol Y. Some books use it, I don't know, some books may use other words, but I'm gonna use Y for it. And it's defined as stress divided by strain. And then we have the definition of stress. Its definition is force per unit area, and the strain is defined as change in length divided by original length. That's the form of Young's modulus. And once you have this Young's modulus, you immediately see that every single quantity that we have written here or that we needed, that we are looking for, it's in this formula. So we just need to apply this formula on these two situations. So let's write it in a little bit more explicit form, and this will give us y equals FL divided by A times delta L. Okay, this is Young's modulus, and it is same for all these three configurations of the wires. Okay, let's try to solve this first part. So in this case, we have the same force. In fact, force is the same for all three cases. So Young's modulus is the same, force is the same. But in this case, we have area also same. So area of this wire is the same as the area of this wire is given. So what I'm going to do, I'm going to separate all those quantities which are fixed. So y is fixed, area is fixed, force is fixed, and this gives me L divided by delta L. Okay. So this is for this wire. But if I look at this wire has the same area as this wire, and the applied force is same. It means that this left hand side is same for these two wires. And if this is same for these two wires, I can apply this formula two times, once on this wire and once on this wire. So when I apply it on this wire, this exactly gives me this form. And when I apply this formula on this wire, the left hand side stays the same because area is the same, applied force is the same, Young's modulus is the same. But the right hand side will change to L1 divided by delta L1, because these are the two quantities which are different for this wire. And L1 is 2 times L, and delta L1 is something that we want to see what it is. So we can solve this expression for delta L1, and delta L1 will be L1 divided by L times delta L. And L1 is 2 times L, so 2 times L divided by L times delta L. L cancels out, and delta L1 is 2 times L, and so the extension would be 2 millimeter. Okay. So if we double the length of the wire, keeping everything same, and apply the same amount of force, it will extend 2 times compared to this original wire. Okay. Now I need to use the same formula for this wire, but I need to look what are the constant quantities between this configuration and this configuration. Okay, so let's see what is not changing in the third configuration compared to the first one. And I'm going to write the Young's modulus formula as y equals F L divided by A times delta L. Okay, if I look at this wire, length is the same, length is constant, but area is changing because diameter is changing. So I'm gonna separate out y, f, and L. So my expression will become y divided by f times L equals 1 divided by A times delta L. Okay, so this is the relationship for this wire. Now I'm going to write this same relationship for this third wire. And for this third wire, left hand side stays the same because we have the same Young's modulus, same force being applied to the third wire, and its length is also same as the first wire. So it should be L2 here, but I'm going to write it L because L2 is equal to L. And the right hand side, we will have A2, this area of this third wire, times delta L2, which I want to calculate. And now I see that the left hand sides of these two expressions are equal, so the right hand sides should be equal, and if I put them equal, this will be A delta L equals 1 divided by A2 delta L2. And so this gives me A2 delta L2 equals A times delta L. And I'm looking for delta L2, so this will be A divided by A2 times delta L. And I know the values of diameter, not of the area. But area is equal to pi times r squared, or in terms of diameter, this is pi times d squared by 4. So if I write that for A2, this will be pi times d2 square, and d2 is 2 times d, so this will be 4 d squared by 4, which is d pi d squared. Okay, so if I calculate a divided by a2, this will be pi d squared by 4 and pi d squared. So pi d squared cancels out, and a divided by a2 is just 1 by 4. And so here I get 1 by 4 times delta L equals delta L2, and delta L is 1 millimeter. So this will be 1 by 4th of a millimeter. So we have two results. Okay, just make sure that you understand how I solved it. And this is the general procedure in physics for solving any kind of problem. That you look for quantities which are, if it's a comparison kind of problem like this one, then you look for quantities which are not changing as you go from one situation to the next. So this was the original situation. Young's modulus was constant, force was constant, and length was constant if you go from first to the third configuration. Okay, so I separated out Young's modulus, force and length, and then exploited this to get this relationship, and finally I was able to find what I needed to find. And you now can see the general result too, that if you double the length, the extension will be doubled. But if you double the area, which means you make the wire thicker, the extension will be harder to produce by the same amount of force. So in this case, you see extension has decreased by 1/4 of the original extension, which was 1 millimeter. So questions? Yeah, just make sure that you understand this process of exploiting these properties for in solving problems. Okay. Two. The third one is related to momentum. This is quite an easy problem, so let me erase this part. So we have different situations, and we have to rank them in terms of maximum momentum. So situation is like this. We have a set of blocks with different masses. So we have first block. It's moving with speed 1 meters per second. The first one is 1 meters per second. The mass is 20 grams. The second one is moving with 2 meters per second speed, and the mass is 20 grams. Okay, I'm using speed, just be careful, because the blocks are moving along x-axis. So since the direction is fixed, that's why I'm using speed. Otherwise, be careful that speed and velocity, what it means, velocity comes with the direction, but here the direction is fixed, so I'm just using speed. The third block is 10 grams in mass, and speed is moving with speed of 2 meters per second. Fourth one, same, 10 grams, and speed is 1 meters per second. And finally we have a bigger one. It has 200 grams of mass, and it's moving with 0.1 meters per second. And we have to rank these blocks in terms of momentum from largest to smallest. Okay, so we are just looking for magnitude of momentum because direction is fixed. All the blocks are moving along, let's say, x-axis, so the magnitude will be m times v. Okay, you don't really need to worry about units here. You can just use the units whatever are given, because the units among all these masses are consistent, because like velocity is given in meters per second and masses are given in grams. Okay, so you don't need to worry about units too. You can just look at the magnitudes. So applied to this one, let's call it P1. This will be 20 units of momentum. Let's not worry about that. P2 will be 40. P3 for this mass will be 20. P4 for this mass is 10, and P5 for this mass is, what is P5? Can someone tell me? 20. Yeah, just be careful, it's 0.1, it's not 1. Okay, so we see if we are supposed to rank them, then P2 has the greatest value of momentum, then we have P1 equals P3 equals P5 greater than P4. Okay, so that's simple answer. You just rank the magnitude of these. So these three have equal value of momentum. By the way, I said just ignore it. In this case, the units will be grams meters per second. Just be careful, they are not kilograms meters per second anymore. Since the mass is given in grams, and I did not bother to change it because they're consistent, like all the masses have the same units of momentum, so it's grams per meters per second. So this is what we are looking for.